thank you very much for the introduction. And so I was talk about. So the title of my talk is Algebra for knots. So this is a bit vague. So let me explain what I'm actually going to explain. So I want to first explain this class of algebra called the quiver Yangian and the representations for general quiver and superpotential. So its relation to knots is via the knot-quiver correspondence that Pilchen Helder explained yesterday. So, so the quiver for the knots, there are the symmetric quivers without potential. But I'm going to first explain the general definition construction for the generic quiver and superpotential. So actually I gave 5 lectures 2 weeks ago. So there I started from a general definition, but I focused on the quivers from Torre-Clavier. So the quiver and potential that coming from this class, they can be both symmetric and chiral. And with potential. So this class has some. This class of quiver and potential has some special property that it's very easy to visualize the representation of this class of quiver. So so that's why I focus this I focus on this class in the lectures, and also this is the class that we first studied. So they have some very nice geometric visualization. So we use the representation of the algebra on this class on the states that are coming from this type of quiver to build this quiver Yangian. And I also explained this algebra as the BPSI. So I'll try to review this part a little bit. And then for the second part of my talk, so this is I want to talk about another construction of a similar type of algebra. Actually, this is an older construction that predates this quiver Yangian, but I realized that it might be also useful for in this knot context during future talk. So that's I decided to just mention this also at the end, second half or towards the end of the talk. So this is different, slightly different construction. So for example, if you look at this this class of Torre-Clavier. So the PPS algebra for this Clavier. So here the idea is that you first translate this information of the Torre-Clavier to the quiver and superpotential, and then build the quiver Yangian from this quiver and potential. So actually, before we did this work, so this is also this work with Longi. And also later. And also some work before. So the idea here is that instead of translating this Torre information to the quiver and superpotential, you directly use the quiver diagram or the dual diagram. And the starting point is the BPS algebra for the C3 case. So there the answer is no. is some so-called alpha Yangian GL1. So then for the general toric labial 3, you try to glue this the building block according to the toric diagram. So that's the logic. So what would be relevant for us is the resolve carnival. So there you can glue 2 alpha Yangian GL1 according to this diagram. So for each of these C3, you have 1 alpha Yangian GL1. So you somehow glue them and use some representation to consistence condition to fix the algebra itself. Right, so this is the plan of the talk. So let me first give a bit of a history. So why we're interested in this class of algebra. So the bigger context is this idea of the BPS algebra, defined by Harvey Moore. So this is the algebra of the BPS states. So the idea is that for this algebra, the elements will be some BPS states in a Hilbert space. Of course, you have to specify what you want to include here. Maybe you want to have local operators, and maybe you want to include volume defects and stuff. And the multiplication of the algebra is given by the so-called fusion of 2 BPS states into a third BPS state. Of course, the whole point of construction is how to properly define first what you want to include here and what do you mean by fusion here. So, and there have been various studies on the BPS algebra, also in different formulation of the algebra. For example, there's the most important one is Koha, by Kentevich and Swiberman. So this definition works for quite general case, in particular also for general quiver and superpotential. And one drawback at that time we feel is that we don't have explicit relations in terms of generators. And there's also this, sometimes it's, for special cases, you can have the algebra in terms of the VOA, or sometimes it's as Yangians. So for both these cases, they are only so they only exist for special cases. So so our motivation. So this is work with Yamazaki. So at the time, the motivation is that we want to have some explicit realization also for more general cases. So there we consider the case of the half BPS sector of the half BPS degree bound states of the type 2A strings in generic toric labial. And then then this word volume theory is given by some link to for quiver quantum mechanics. So this quiver and this potential that come from this toric labial 3 has some special property, so that when you consider the moduli space of the semi-stable quiver representation, and you look at the toric fixed point, the end result is that they can be described by certain 3D colored crystals. So in general, if you're a mathematician, when I start to talk about this, color crystals, you start to take out your laptop and or phones and start to or fall asleep. But I want to just very quickly review this part. But the real definition you can actually see later. That I actually have a very precise definition of what I mean here. But before that, you can. There's one easy way to see this. So for the C3 case, so if your Tori club is a simplest case, when it's with C3, then this quiver is just this one, as this 3-looped quiver with this potential. And then this class of the 3D color crystal is just the set of plane partitions. So you should be at, probably this is a more familiar territory. So the generating function for all these plane partitions is given by the Macron function. And then this Macron function just is the BPS partition function of the D0 branes attached to 1 D6 in this class. And then for the general Tori Clavier 3, this is it's a generalization from this plane partition to some more complicated crystal structure. And the different, so here you only have one vertex that corresponds to the fact that you only have, there's no color for these plane partitions. So for the general Tori Clavier 3, you can have more than one vertices. So the different vertices correspond to different colors for the atom in this. So another idea is that to construct this algebra, we want to focus on the so-called spherical part of the algebra. So meaning that instead of considering a fusion of two general BPS states, we consider the special case where one of them is a so-called a unit BPS state. So then if you start from a generous BPS state and then you fuse this together with a unit one, and you can realize this process by having your BPS algebra acting on these states. So in this construction, your BPS tuple space will be a Verma module of the BPS algebra that you want to construct. Okay, so then in this class, we already have a description for this class of 3D color crystal as BPS states. And then we first try to fix the action of this BPS algebra that we want to find on these crystals. So this action is fixed by demanding that it should reproduce the fusion process. In particular, you want this action to be cyclic. That if you start from any state, you want it to, by applying this BPS algebra repeatedly, you can reach any other states. And you also have to satisfy some conditions such that you always land on the allowed crystal states. So once you fix this action, then so this is a infinite dimensional space. So once you fix the action on any states, basically you can find the relations among all these generators. And I forgot to mention that. So this is just a racing operator. So we also introduced the Cartan and the lowering operator. So we extend the definition of the original BPS algebra. So once you fix the action, then you can find the relations among all these generators. So So then your algebra is just defined by the free algebra divided by all these relations. So in some sense, you bootstrap your BPS algebra by its representations. So this is and so this. So this crystal basis turned out to be a very nice basis. So that in the end, the algebra we fix, at least for the quadratic relation, they have a very simple and universal form. So let me just write down the quadratic relations for you. So we have three for each vertex in the quiver. We have three family of generators. So we have the racing operator, and the Cartan, and the lowering operators. So each of them is you think of them as packaging all the modes of the algebras here. So the most important ingredients for this algebra is a rational function that we call binding factor. So it's a rational function for each pair of vertices in the quiver. So this is not symmetric. So in general, this is not the same as the function from A to B. So to define this, we have to define something else first. So for each arrow, so this is the arrow from A to B inside the one. For each arrow, we introduce a equivalent weight. So and then, so remember we have this superpotential here. So this is a sum over some monomial of the arrows. So for so this condition will give the path equivalence for the arrow. So this can so for example, if you have a potential like this, I1, I2, I3, then if you take the derivative of the potential with I1 to 0, then you get the equivalence between these two paths. So for each so now for each term in your potential, you get a constraint on the weight here. So for each loop in your quiver, you sum over all the weights of all the arrows along this loop, and these have to be 0. And now this bounding factor is defined by so this is the bounding factor from B to A. So you look at all the arrows from B to A. So each arrow give you a factor. Each arrow from B to A give you a factor in the denominator, and then each arrow back from A to B give you a factor in the denominator. Okay. So then now I can write down the algebra. So first you have the pattern.
Wait. So you said that this algebra is derived from D-branes and capital string theory, world volume quantum mechanics. So are these arrows, should we think of them as some fields in the quantum mechanics?
No, this is so this. You should think of, you're looking at the moduli space of the so in this quiver quantum mechanics, for each arrow you have a arrow bifundamental. So this is the quiver representation. So you're looking at the moduli space of this quiver representation, and then
the arrows are bifundamentals?
Yes. So each vertex corresponds to a gauge group. So this is the bifundamental transform along this. So then you're looking at the so this gives you a quiver representation, and here you also have the. Yeah, maybe I should have explained here, but so then this essentially this gives you a representation of the Jacobian algebra, so which is the path algebra divided by the F term constraint here, and then you use the D term that gives you the stability condition to translate this information on the representation to the ideal of this Jacobian algebra.
And these weights that you introduced, these conditions sounds like
yes, exactly.
Are symmetry, so these are charges of these poles?
It's not R chart. It's the so this one. This is the input for chiral multiplet. So there's a scalar there. So this is the mass of the complex mass of that scalar of the inside this.
So then you can have negative mass. So they add up to zero.
Yeah, I mean for the algebra, I can even think of this as some formal parameter that I use to span. Of course, when you need to, depending computation that you're doing, you need to specify it to be complex. So this is the Catan, and then we have a raising operator and lowering operator here. So you see that the information of the quiver doesn't enter into these two relations. So these two relations are universal for all quivers. And then so there's some plus minus signs, that some statistics factors that I'll gloss over here. I mean, there can also be some factors here.
So are these relations for the nodes which are connected by an arrow? A and B need to be connected?
If they are not connected, then it's 1.
I'm asking about this relationship. A and B are connected by an arrow? That's
the first two?
Yes.
The general, this is for general A and B. So, I mean, it doesn't matter whether they're connected. So this relation, they're true for any equipment. And here you see that if there's no arrow here, then this factor is just 1. And then, okay, this already get more complicated. So you see the information of the quivers enters via this bounding factor and also actually via these statistic factors. And then, one thing that I find very intriguing is that this E relation is actually very similar to the precise E relation. And then the precise F is this inverse. And the FF is the same here. So, so this is the relation that's true for. In the beginning, we want to say that this is true for any quiver and superpotential that come from this Torrey club L3. And later, I want to say that this is actually true for any quiver. And so this is the quadratic relation that we first obtained by this bootstrapping procedure. So that procedure also allows you to write down all the higher order relations. But those are much more difficult to fix. And also the form of the higher order relations will depends on the quivers and potential. So I won't have time to explain the higher order relations. And also, for symmetric quivers, you can also fix you can also introduce the co-products for the algebra. So those is also yeah. So this you can see the paper of with Galakov and Yamazaki. Any questions before I move on to the general quiver page? Right. So now I want to explain the case for the general quiver in order to explain the connection to knots. Yeah. So as I said, so the relation we wrote down earlier, we want to say that they're true for arbitrary quiver, and it only has meaning if you can also construct the representation for arbitrary quiver. So, as I said earlier, that without any explanation that for the Torrey club L3 quiver, the representation they are given by certain class of 3D colored crystals. So the question is, instead of these crystals, how do you describe the representation for the general case? So So first I want to mention that the concept of the framing. So a framed quiver for a given quiver, the framing is means that you introduce another vortex. That's called labeled by this infinity sign, and then there's some arrows going from the framing vortex to some vortices in that's already in your quiver, and some arrows back. So this frame quiver is just the original quiver with additional vertex. With a bunch of arrows. So you can actually package a lot of information into the framing here. You can you can put your stability condition here, and you can introduce line defects. I mean, you can actually package many information here. And so for our purpose, we just need to consider the simplest framing possible. So we just have one arrow going from the infinity to a particular framing vortex. Let's call this vortex framed vortex, and put a hat there. So for the Torrey-Clapeyron case, this corresponds to the non-commutivity chamber for the for this deep brain bound states. So now we define we need a definition of the Jacobian algebra for the equivalent potential. So this is just the path algebra divided by the path equivalence that's given by this superpotential here. So this path algebra is just the elements is just the path that's given by the product of all these arrows. And the product of the paths is just by the path concatenation. And so this path equivalence I already explained earlier. And then now for this framing, we're considering the subalgebra of this Jacobian algebra that consists of all the arrows that start from this framed vortex. So all the arrows up to path equivalence. So all the paths inside this subalgebra is they all start from this framed vortex. So now the point is that for each framed quiver, so in this philosophy, for each framed quiver, that will correspond to a representation of the this Jacobian algebra. Sorry, we want to think of this. Each framed quiver will give you a representation of the quiver Yangian that I wrote earlier, and what you build from this framed quiver is finite codimensional ideals. Of this Jacobian algebra. And then this ideal has to be inside this Jacobian subalgebra that you start from the framed vortex. This is the statement. So let me summarize these ingredients here, and then also its realization for the Torrey-Clapeyron 3 quiver, and why there you can see that you have this 3D crystal realization. So here I write general equivalent potential, and here I write the toric case. So we want to consider the Jacobian subalgebra here. So I didn't explain earlier, but the equivalent potential that comes from this toric Laplace has some special property. And in short, so each arrow appears exactly twice inside this superpotential. Once in a term with a plus sign, and the other time with a term in a term with minus sign. So this property makes sure that you can repackage the information of the equivalent potential into a periodic quiver. So, meaning that you're drawing this quiver periodically on R2, and along each loop, the arrow goes along the same way. So, and then in the fundamental domain, each phase, so this is the collection of the phase. Each phase corresponds to a term in the superpotential. So the superpotential information gets translated into the information of the phase here. And so now you have a periodic quiver, and then you uplift this periodic quiver, start from a vertex of colored A hat. So this uplifting gives you a three-dimensional crystal. So that's this guy here. And then, so the element inside this Jacobian subalgebra is all the paths starting from A hat and up to the path equivalence. So here is captured by an item of color A. So this is some particular answer here. So this is A and some arbitrary vertex here. So now we want to the states in the representation of the quiver Yangian. So they are given by the finite codimensional ideals of the full Jacobian algebra, and then this ideal is inside this subalgebra. So it's codimension NA. So this ideal will correspond to this full crystal. Let's say. With some subcrystal near the origin removed. So you're removing a subcrystal with this number of atoms. And then, so because this is an infinite dimensional ideal, it has a finite codimension. So it's easier to look at this the complement of this ideal. So then the complement ideal have this dimension NA. So that means that here we want to look at this T, the subalgebra near the origin that you removed. So in the crystal melting language, this is called molten crystal. With this number of atoms. So the plane partition that I drew earlier, that will correspond to this molten crystal in that case. So now I can write down the representation here. So I use this notation to denote a complement of ideals. So it will have a bunch of, so each of these states will have a bunch of paths up to path equivalence. Okay. So each such state is the eigenstate of all the carton. with this eigenvalue function given by, have a very nice factorized form. So it has a factor that's come from ground state. So this is depends on the framing, and then for each pass that's inside this ideal. So I use the same notation that normally when I write atom, I just use this box with a color inside. So all the color, so this is the eigenvalue function for the color A. So all the other color also contribute. So for each pass, after pass equivalence of the color B, you will contribute the factor in terms of this binding factor earlier, the B to A, and then with the variable shifted by the equivalent weight of this. I should define this weight of a path is just a sum of all the weight of the arrow along this path. And then the raising operator and the action of the raising operator and the lowering operator, they are completely fixed by this eigenstate function here. So this is the so you're for any ideal here, you're looking at the all the paths that you can add to this complement of ideal, such that the final state is again a complement ideal. This is the residue of this function at the pole that's given by this equivalent weight here. And similarly for the lowering operator, you're looking at the place where you can remove a path from this complement of ideal. So the point is that all this is automatic with this choice of eigenstate function, and then the definition of the binding factor there, and this loop constraint that's imposed by your superpotential. All this is automatic. So you don't need to check whether this is I proved in this paper in 2003 that with these choices, is automatically only give you it only give you the complement ideal as a final state, and also it capture all the final states you need. Okay, so now this I reviewed the part that's about the quiver Yangian representation for arbitrary quiver. So now for the knot. So as was explained by Future and Helder yesterday, for a knot, you get a quiver or maybe more than one quiver via this knot-quiver correspondence. So the starting point now is this quiver that you already have via this knot-quiver correspondence, and there's no potential. And all these quiver are symmetric. So now you can just plug in that information of the quiver into the definition and the superpotential. Then it just work from there. So the generating function for the dt invariant for this quiver representation, it has a closed form. So the C is the adjacency matrix. So this the X is all the fugacity for all the vertices here. So this you can rewrite into the implicit exponential of packaging the dt invariant here. So now you translate this into the generating function for the for the representation that's given by this this simplest framing. So the translation is the following. So D is this dimensional vector for the framed vertex here. So now the undefined limit. So this will be directly what you compute from the algebra, and then for the refined case. So that takes more work. I mean, there's also some specific prescription that you have to find to reproduce the refined case. So I think actually here there's still quite some work to do to make it the whole thing more systematic. So for the last 10 minutes, I want to explain this the gluing story. So so the basic idea is, as I explained already earlier, that suppose you look at this toric Clavier-3 case. So instead of going via this quiver and potential and then use the quiver Yangian, instead you just look at this the quiver diagram, and then you think of this toric Clavier as a gluing of multiple C3. So for each vertex here, you have a C3. And for each C3 earlier, we have they correspond to this quiver. And these algebras is called alpha Yangian of GL1. So the idea is that for general toric Clavier-3, if you think of it as a gluing of multiple C3, for each C3, you have a sub-algebra of this in alpha Yangian of GL1. And then for each internal lat, you need to introduce additional operator that transform as bimodule with respect to the two alpha Yangian of GL1 at these two ends. So I think you can do this for general toric Clavier without the full cycle. But actually, it's quite tedious, so we actually only do it, have only done it for these two cases. So this is this picture here, and then there's some I mean, there's some choices for the different type of representation that you choose for these gluing operators here, but this is enough for us today when we consider the knots. So this will be the result quantifold. So again, when we want to fix this algebra, we use this idea of the bootstrap. So you first construct the representation. So in some sense, I think this construction is actually more non-trivial than the quiver story, because for the quiver story, you already have this the representation in terms of the 3D crystals there. So here we actually really build this representation from scratch. So for each C3, you have this is your algebra, and the representation is the plane partitions. So when you glue, so now you're gluing two plane partitions together. So on this side you have the set of plane partition. On this side, on this side you also have a set of plane partition. And then you glue them by having a row of infinite long, and then the cross section is the Young diagram. So accordingly, you want to so remember for each end, you have all this raising and lowering operator that add or remove boxes from these two corners. So for this long row, you want to also introduce a raising and lowering operator that add or remove a long row of with cross section, just one box. So, but then you need to you need to make sure that the interaction between this additional operator. So first they have to transform as bi-module with respect to the two alpha and J1. They also have to interact nicely with the existing sub-operators in the sub-algebras. So after all the dust settles, you have a nice representation, and then you fix the action of this the algebra on this representation that you just created, and then from there you obtain the final algebra. It's actually quite long and a bit tedious, but surprisingly, in the end, it worked. And it reproduced and the counting reproduced the BPS partition function for the for this case. Yeah, I think this is all I want to say here. I think I overshoot and went too fast, but maybe you can ask questions. I think one obvious question is that, so here you have this result conical. So the quiver that corresponds to this case is that this quiver. So you have two vertices and then this pair of arrow, and the superpotential is like this. A1, B1, A2, B2, minus A1, B2, A2, B1. So, and then you can plug this into the quiver Yangian, so you have algebra. On the other hand, you also have another one, and you can ask what's the relations. So one point to know that this is more suited to capture the NCDT non-commutative DT chamber, and then all the chamber that's finitely away from this NCDT chamber by doing the wall crossing. And so here the representation is in terms of this. So for this chamber is this pyramid. So if you do it, if you wall crossing another step, so you have finite steps. You have this pyramid with a long ridge, and this number is the number of steps that you cross the wall here. But here, this is given by this glued plane partition. So this is more suitable for the topological strings sector. So in some sense, these two are infinitely far away. So, but this is closer to the topological string sector. So that's why I find that maybe this is more also will have some its place in this not in this knot study, but it's a different, totally different algebra from the quiver Yangian. Yeah, that's it.
Okay, so any questions?
So in knot-quivers correspondence, like there can be different quivers associated with the same knot, right? So I was wondering how the quiver Yangians for quivers that relate by linking or unlinking.
Yeah, so this is something that I'm working right now, so I can explain to you a bit later, but I think I shouldn't say much here.
Okay, any other questions? Okay, so if not, let's thank Wei Li once more.